Hello and welcome back to Water Resources. What we're going to talk about here is hydrographs. Hydrographs are the way that we display river discharge data, and they're used in a lot of different analyses on stream flow and other water resources issues. So let's first start with the basics. A hydrograph's a graphical display of stream flow or stage through time. So normally, a hydrograph's going to graph on the y-axis discharge. We defined discharge in an earlier lecture in this module. Sometimes, however, stage is used here, and stage is stream depth. And depth is used in that case as a proxy for discharge because discharge data was unavailable or not obtained. It takes more work, fancier equipment to get discharge versus stage. But your standard USGS hydrographs, if you go on the USGS website, are going to show you discharge. All right, so flow, usually expressed as discharge in volume of water per unit time, such as cubic meters per second. We went over that in detail in the first lecture of this module. And stage is measured relative to some datum that's established at the site. It could be above sea level, but often it's just an arbitrary datum, so many feet above some arbitrary benchmark. All right, so before we move to the next slide, let's just take a quick look at the hydrograph here. So we already mentioned the y-axis. The x-axis will be the time axis. Some hydrographs will have precipitation plotted on them. Usually the precipitation hangs from the top of the graph. So here you see we had 4 time units of precip. If these were hourly data, 4 hours of precip, and the third hour was where we had the peak. And the secondary y-axis is for the precipitation in this case. We can separate out the flow components in a hydrograph. The most basic separation would be base flow. So here, base flow is your average everyday flow. Obviously, we've talked about this in the past. Base flow is mostly contributed by groundwater inputs into the stream. And then if we have a big rainstorm, like shown here in our precipitation graph, that can induce surface runoff, and the portion of the hydrograph above the base flow line would be storm flow. Now I've kept this simple and I've kept the base flow line horizontal. Sometimes the base flow line is at some angle. Maybe we have one storm following another, so previous to the hydrograph shown here, maybe another hydrograph was already descending, and we had another storm and it peaked the rainfall back up and back down. So there are different situations where you could get angled base flow. All right, so let's look at some of the more technical elements of the hydrograph. The limb here from base flow up to peak discharge is called the rising limb. The limb that goes from peak discharge back to base flow is the falling or descending limb or the receding limb. So 3 terms here, all more or less synonyms that are commonly used. So people will say falling limb or descending limb or the recession or receding limb. All essentially mean the same thing. We've got our peak precipitation, we've got our peak discharge. The difference between those two is the lag time. So short lag times are part of the definition of a flashy discharge or a flash flood. This hydrograph would be, we don't know the exact time units here, and we don't know the exact discharge units, but generally speaking, a hydrograph like this that has a really steep rising limb, a really steep descending limb, and a short lag time would be considered a flashy hydrograph. So this would represent a flash flood. More or less the same thing here. The one thing that I want to show is here we do have that angled base flow line separating storm flow from base flow. And in this case, what's going on is we have this big flood come through. That flood is associated with a large rainfall. And maybe this is in the spring of the year when the soils are open, not frozen, but there's not a lot of evapotranspiration going on. So a relatively high percentage of the infiltration can move beyond the root zone and start to percolate and recharge the groundwater. In that case, the storm, the part of the precipitation that is not the storm flow that got percolated into the groundwater may raise base flow. So the base flow may end up higher after that storm. And then it may come back down through time. This can happen over a period of days, or I experienced a large flood in a system that I worked in quite extensively in southeastern Minnesota in 2007. It was probably somewhere between 200 and 1,000 year flood with about a 20,000 year recurrence interval on the rainfall, which nobody even knows what 20,000 year recurrence interval on rainfall means, but that's technically what it calculated out to be. That actually raised base flow in a lot of our streams up there for about 2 to 3 years. Base flow was about 25% higher than it had been. So we had a lot of recharge from that event. Here's a non-flashy hydrograph. Perhaps we could call it a normal hydrograph. Although I am a little hesitant to say what is normal. There's a lot of variation. But at any rate, it's definitely non-flashy. We've got our peak discharge, our peak rainfall here with the red histogram. And then we have a very gentle rising limb and a very gentle falling limb and a low peak discharge. So if we just compare this with the previous, here we had a high peak discharge, and it looks like we had a relatively about 50 centimeters peak precip, 50 centimeters peak precip. So what you'll notice here is we have the same amount of precipitation over the same amount of time in these two hypothetical hydrographs, but very different responses. If we integrate the area or just calculate the area under this curve, that would be the total discharge for the storm. So we could calculate how many gallons or cubic meters of water discharged over this time period. There would be a lot more here for the same amount of rainfall than there is here. What happened to the rest of that rainfall? It obviously didn't end up in the stream. The difference here between that flashy hydrograph in the last slide and this one is all the places that water can be intercepted, stored, evapotranspirated back to the atmosphere before it gets into the stream. That's part of what makes some watersheds, forested or prairie watersheds, so non-flashy, is that there's lots of places where the water can sort of be held up and retained instead of drained through the stream. This is another hydrograph separation. Here we've got our base flow again. Our storm flow would be everything above the base flow, but in this example the hydrograph has been separated out below this maroon line into a through flow component and an overland flow component. So you should remember, probably, but you should, and if you don't, you should go back and review these in the watershed factors and other lectures earlier in the semester, where we talked about the hill slope drainage pathways that water can take through the soil. So some water can drain as through flow. Once the soil becomes saturated, we get overland flow. We can separate out those components of the hydrograph. And what you see here is our flashiest hydrographs, our flashiest floods occur when we get overland flow. Now, if you think about it in your experience, if you live somewhere else or have experienced a different climate, this may not be your experience, but if you live in most of the central part of the U.S., certainly most parts of Missouri, we have soils and vegetation and other things that often absorb most of the rainfall. We don't see overland flow until it rains pretty darn hard or pretty darn long, or both. So overland flow is relatively rare. It's more common, say, here in southwestern Missouri, where we have thin clay soils, than it would be in northern Missouri, where they have thick glacial soils that have a high permeability. So this overland flow component, once it gets activated, really is what contributes to a lot of our flashiest floods. All right, urbanization often causes hydrographs to become flashy because of the impermeable surface that's introduced in the urbanized land use. So think about an area that might have been grasslands or forest, and you come in and you build roads and homes and businesses and parking lots. All that impervious surface that causes water to run off and keeps it out of the soil where it can soak in and be stored and slowly released back to the stream. So all that water, basically what cities do um, with their stormwater runoff is try to get it as fast as possible into a storm sewer and then get that storm sewer flow directly into a stream somewhere. So there's not a lot of effort to capture that water in between and hold it for a while. And so it all gets into the stream at once. You get a big flood, the flood passes and it's over. But that short duration flood is really high magnitude and can cause a lot of damage. Here they're showing the effects of urbanization. An earlier stage of urbanization was represented by the dashed line. So the peak discharge before, we have a longer lag time and a smaller peak discharge. As urbanization progresses and more impervious surface is introduced into the watershed, we get a shorter lag time and a higher peak discharge. So flashier hydrograph. We've shown this graph at least once, if not a couple of times in previous lectures. It's that hypothetical watershed where all else is equal, but we look at what the hydrographs are based on different land uses. And of course, forest, and we could put prairie out here too, have that least flashy discharge. Urban is the most. Question to ask yourself is why is an agricultural area more flashy than, say, a forest? Isn't there a lot of vegetation there? Well, there is, maybe. You think about it, you've got a cornfield, but a cornfield has a lot of bare soil. Farmers, when they're growing corn or beans or any other crop, generally they're trying to keep everything that's not the plant they're trying to cultivate is considered a weed, and so it's killed with herbicides or other means to keep all the soil in between each corn plant or each soybean plant bare earth. That limits the opportunities for interception of the rainfall. Also, the tilling of the soil for the agriculture reduces the amount of organic matter in the soil, and organic matter is part of what makes soil act like a sponge and hold on to water rather than rapidly draining it. So even though an agricultural region may not be introducing a lot of new impervious surface to a watershed, it is introducing a lot of bare soil that promotes a faster rate of conversion of precipitation into stream flow. So the questions I leave you with on this slide are, which of the hydrographs is flashy? Hopefully you can answer that question based on this lecture. Explain the difference in hydrograph response between the urban and forest hydrographs. I've discussed that. And answer, why is the agricultural hydrograph intermediate between the urban and forest hydrographs? And I want you to think in terms of the 7 watershed factors. So I gave a quick explanation for why urban areas are flashy, why agricultural areas are more flashy than forest, why forest is less. And I did that in terms of some of the 7 watershed factors. Now, not all 7 watershed factors come into play here, but if you go back and re-listen to my explanations on those, you'll see I talked about soil, I talked about land use, talked about maybe climate a little bit in terms of how hard and how fast the rain comes. That can vary with changes in climate and so forth. So think about in terms of answering these questions in terms of the 7 watershed factors. That's the way I'm going to phrase those questions on quizzes or exams. And with that, we'll close out the lecture, and we'll see you the next time. Thank you.